Welcome back to the last week of ECE 441A, 541A. You have quite a few things due on Wednesday of this week, on the 5th, and in anticipation of that, today is full, but tomorrow I blocked down some time ahead of time so that you could come see me if you have last-minute questions on homework 9, homework 10, your project. Hopefully you won't have questions on the TCE. The TCE, I hope that you take a few minutes to complete that. That is helpful information. That's one of the only ways that I obtain feedback from most of the class in terms of how the class is going, how you felt that it went, and are there ways that it could be improved. The final exam is, a week from tomorrow. The final exam is at 10:30. It's on a Tuesday. It's not a Monday, Wednesday, Friday. It's a Tuesday. The final exam is at 10:30 to 12:30, and I have posted a little bit more material in anticipation of you preparing for the final exam on D2L. There's a list of topics post exam number 3 that you need to get comfortable with for the final exam that will be on the final, and the final is comprehensive. So you have to go back to day 1 and review and get ready for the final exam. And I've also pulled some previous material from an earlier exam number 3 that we didn't have on our exam number 3 dealing with Bode plots, and in particular system identification from a Bode plot, and another one is finding phase margin and gain margin from a Bode plot. Today what I want to do is really summarize what we talked about last time, chapter 11. I hope you had enough material to actually complete homework 10 if you wanted to over the weekend. I want to summarize what we talked about last time. That's coming from chapter 11, the full state feedback design. And then we'll get into comparing these two controller strategies. We have root locus and Bode plot based controller designs in what I'm calling the output feedback configuration, where our controller is in Cascade with the plant. And then we have full state feedback, where we're actually assuming that we can go in and measure or have access to all of the state variables in our system and then scale those and add those up to give us the input that we want. Let's start with our summary of full state feedback, and I'm going to go through this maybe a little bit quickly. You probably won't be able to sketch all of these diagrams, but I'm really hoping that you can start to get all of this clear in your head, or what it really sort of means. And the assumption with full state feedback is that we have the entire state vector. Look at where the feedback path is actually coming from in full state feedback versus output feedback. The full state is being accessed, the x of t, not the y of t. I'm assuming that I can measure x sub 1, x sub 2, x sub 3, scale those with a gain k, and k in general is a matrix. I know it looks like just one variable, but it now consists of some matrix of adjustable parameters that are inside that k. And we are also assuming that we can weight or prescale the reference input. And you could sort of view that as like your k sub pf in the lab. You were able to adjust that k sub pf to be 0.015 or 0.0 whatever it was, maybe 0.15, 0.075. You could adjust that k sub pf. That's like adjusting capital N here. Can we adjust that in to account for, we're actually changing gains in the overall system by the adjustment of that full state feedback matrix, capital K. But this is our system. It's very high level. There's in that integrator block are however many integrators we need. If our system is 10th order, that integrator block has actually 10 integrators associated with it. A is our 10 by 10 system matrix. B depends on how many inputs we have, and C obviously depends on how many outputs we have. But all of those now, that highlighted blue area is our system or our plant. That's now our plant. We're going inside that plant in the sense of we're accessing the full state vector and not just the output, scaling that and feeding that back to form part of our input. Our input is right there. U of t is now the output of that leftmost summing junction, which is now made up of minus k x of t plus n r of t. As I just said, there's the full state feedback. The input to the system has two pieces. If you weren't applying an input, an external or a reference input, then you would be changing the dynamics by this full state feedback gain matrix K. And that might be something that you want. Maybe your system is really designed to respond to initial conditions, and you want to change that system's behavior in terms of how it responds to initial conditions by the appropriate selection of that full state feedback gain matrix K. In this particular block diagram, typically what you're wanting is injecting an R and having Y follow that R. Meaning, you want Y to track or behave like what R looks like. You want there to be almost a one-to-one or a matched relationship between what you put in and what you get out. And that's what I'm trying to say here. Our typical goal is we want Y of t to track or follow the reference input R of t. Or ideally, you now have a DC gain of 1 between the reference input R and the output Y. And when we say DC gain, now you can start to think about what that means. That now means, our closed loop transfer function, capital T sub C of S, and you can now find the closed loop transfer function many different ways. You could go back and simply do it with A, B's, and C's. You could expand this and do Mason's gain from R to Y with all the different paths and loops. But now you want that closed loop transfer function when S is equal to 0 to equal 1. And here it is algebraically in terms of those matrices that are making up our system. We have the A, B, and C. We're assuming that we do not have a direct feed-through term from the input U to the output Y directly. We simply go through B, then this integrated set of dynamics, and with full state feedback, we are actually changing the closed loop system matrix from what it was when it was just the A. Hopefully you can see that, with the appropriate choice of K, I can now manipulate the way this system behaves. I can change A into F. And if possible, what you're trying to do is adjust this N, which is, like I said before, consistent with your K sub PF in the lab. Select that to produce the appropriate DC gain that you want, which in our case typically is to have the DC gain equal to 1. So that's the summary of full state feedback with a reference input, let's now compare all of these different control strategies. And in a sense, this is a review for the final, sort of. To get to this point of control, we have to be able to do quite a bit of the preliminary material. The material on exam 1, the material in exam 2. Exam 3 is the output feedback controller design using root locus strategies. Now we have not only root locus control strategies, we have Bodie plot control strategies. How do we adjust the magnitudes and the phases to give us the appropriate Bodie plot shape? And finally, we now have full state feedback control. Here's an all-integrator block diagram, and you should be able to produce this given a system of differential equations. You should be able to draw that. Or contrast that with, if I now give you this block diagram with all of those variables erased, can you produce a state space representation? Or can you create the transfer function between u and y from this description? I could give you this in many different ways. I could give it to you as a second order differential equation. I could give it to you as two first order coupled differential equations. I could give it to you as this block diagram. But you now need to be comfortable finding either g of s or the a, b's, and c's. Here, most of the work is done for you, but how do I find, if I was given this unlabeled block diagram, how would I find a state space representation? And notice I said a state space representation because it's not unique. But how do you go about finding a state space representation from an unlabeled all-integrator block diagram? What's the first step in general? I thought everybody was supposed to bring their VR headset and erase whatever I said to erase. So if you put on your virtual reality headset now and don't see the labels on this diagram, how would you put those, or what would be your first step in finding a state space representation? Put labels on it. And how do you label it? So now you pull out your crayons, sharpen them, take a little bit of time to think as you're sharpening the crayon, and now you say, okay, I need to label this diagram. What's the one, I think, statement that I said you could do to essentially generate a state space representation? Put labels on it. Yeah, now we have labels on our forehead, tape on our forehead with our names. That would be good. Maybe I should have done that in the first of the semester. Then I would know everyone's name, right, Jake? Yeah. Anyway, how do we find these state space representations? What am I looking for? I'm just looking for a one sentence. Assign, I'll start it for you. Assign the outputs of the integrator blocks as, fill in the blank, state variable components, right? Are you guys playing with me? This you need to know by the final. If this was not labeled, you would simply say, oh, let me label that rightmost integrator's output x sub 1. Let me label the next integrator's output x sub 2. And then I immediately know what x1 prime and x2 prime are equal to. And to find the state space representation, I need to find an expression for x1 prime and x2 prime in terms of x1, x2, and u, and that's now available to me now that I know what x2 prime and x1 prime are equal to. Is that clear? We now know how to find a state space representation. or at least we've sort of found it. Can you fill in the block or the blanks? I've already given you that A is square. That's always going to be square. What's the top row of the A matrix look like? Are there any non-zero entries in that top row for x1 prime? x1 prime does not have x1 associated with it, does it? Directly, but it does have x sub 2. Does x1 prime have an input directly connected to it or coming into it? In fact, there's no summing junction there, but I could have put a summing junction between x2 and x1 prime. Question? So now, is it supposed to be a -1 or a +1 for x1 prime? So it's negative feedback, but remember where my negative feedback is coming in this particular, this is the open loop block diagram. Where is that -1 coming into? It's the input, but what's the output? So you were getting ahead. You were looking at x2 prime. x2 prime now is what? What does it equal? Does x1 enter into x2 prime? Now you're simply saying, what are the inputs that make up x2 prime? I have a u making up x2 prime and a minus x sub 2 and no x1. Is that clear? And what's this missing piece up here? I don't have a direct connection of my input u into my x1 prime. But that could all have changed if I would have modified this. I don't know why I'm doing this, but let's say that we did that, and I put this in there with -7, and maybe I pulled this off and said, here's an 8. Do you see how I could change x1 prime to be quite more detailed or involve more information? And I could also feed x1 back into x2 prime and give another non-zero entry in the x1 or x2 prime location. So now I'm going to try to get rid of this so that when you're looking at this, preparing for the final, you don't accuse me of making more errors than I already have. I'm really getting particular here. Okay. We finished with this. Do we have, well, are we done? No. What's y? How do we create y of t? Now it's the summing junction that combines all of our state variables and inputs. In this case, it only has one state variable that is making up y. Our C then matrix is 1, 0. Here is our system matrix A, and there's our input matrix B. Now we can do a cheer to find G in terms of A, B, and C. G is C times Si minus A inverse times B. You can plug in the appropriate parameters for C, B, and Si minus A, and forming the inverse of a 2 by 2, that should be very straightforward to you at this point. You simply interchange the diagonal terms and change the sign of the off-diagonal terms, and divide by the determinant. What's in curly brackets is 1 over the determinant, and that simplifies because one of those off-diagonal pieces was 0. That annihilates that product. And I now have 1 over s times s plus 1. And hopefully you can see that the C matrix, 1, 0, times the adjoint matrix times B, which leaves us 1s, is only going to give us a 1 when we form that product of vectors. The output row vector and this adjoint input matrix product of 1s. Our transfer function now is 1 over s times s plus 1. And you could have obtained that using block diagram algebra, replacing the integrals with their frequency domain equivalent, 1 over s, and finding the transfer function between u of s and y of s. I hope you can see that now you can just pull out a napkin and start reviewing for the final. Somebody can give you a question or a block diagram, a transfer function, and you can just start going. With output feedback, if we now have our system still in that blue highlighted area, with output feedback, we're introducing a cascade controller, a G sub C of S, a ratio of zero factors and pole factors and a gain in this forward path. We're not doing anything other than feeding back the output with a negative gain. We have negative unity output feedback. We're directly comparing the reference input R with the output Y. That error signal, if you wanted to call this an error signal, that now gets filtered by your controller, G sub C of S, creating an input U, and that U drives your system. And typically what we want is we want Y, the output, to follow or track R. And in this case, with G sub C of S, we could actually change the system type if our system wasn't already the type that we want, because we're not messing with feeding back anything in that cascade forward path. We have G sub C times G. With full state feedback, in comparison, look at the difference. What's different in this block diagram? Do we have a cascade compensator? What is U? What makes up U? Here we're in the time domain, but that's not that critical. You can go frequency domain if you want. But the controller now is not immediately preceding U, is it? U is now made up of scaled versions of each of the state variables and the reference input R. We're measuring actually two different unique variables, whereas in the output case we only were measuring x sub 1. Now we're measuring x sub 1 and x sub 2 independently, adjusting those signals, scaling them, and having them form the input command U into our plant. If you have this and that memorized, if you have your headset on still, maybe you could just put those both in your VR headset so that you can see them side by side. Is this comparison fair if we're comparing output feedback with full state feedback? If I ask this on the final, is this a fair comparison? Not is this a fair final. Is this a fair comparison between output feedback and full state feedback, could you tell me yes or no and why? So a yes or no is a coin flip, right? But the why is the important part. What is your thinking or feeling? Is it fair to compare this control strategy with this? Is it fair to compare output feedback with full state feedback? Anybody brave enough to volunteer an answer? Or do we want to do thumbs again? We can do thumbs on yes, no. So let's do that just to begin with. Is this a fair comparison? Yes, thumb up. No, thumb down. At the count of 3. Okay? We're at the end of the semester. Hopefully we remember this little game. 1, 2, 3. We're kind of mixed. Okay, so we're not clear whether this is a fair comparison or not. It's not really a fair comparison. No, not really. Full state feedback assumes that we have access to the entire state vector, x1, x2. If this was a 10th order system, we would now have 10 independent variables that we're measuring and scaling those in instantly. We're not having to filter those through just one signal, output signal. In the output signal, sometimes we're actually trying to reproduce maybe the velocity if the output was position. We can do that. We can kind of create a velocity signal by the appropriate signal processing in our controller and then scaling that. Here, we're assuming we have access to everything. If this was an internal combustion engine and our system representation had internal temperature as a state variable, we're assuming we have access to that and we can feed that back to adjust the dynamic behavior of our system. So it's not really a fair comparison, but let's move forward and see what actually happens when we perform a controller design for both particular situations. Output feedback and full state. To do that, we need some design specs. Suppose we have a steady state error specification saying if I put in a constant, I want your system, after the transients have disappeared, I want the output to track with 0 error my input. And really we have two different concepts to clear up in that one design specification. In the output feedback, all we have to really do to guarantee that is to make our system at least a type 1 system, and then make sure our controlled closed loop system is stable. Boom, that's automatic then. We have a 0 steady state error if we can have a type 1 system. What's a type 1 system? One pole at the origin. Type 2, we have 2 poles at the origin. Type 0, we don't have a pole at the origin. In what? In our plant or in our controller, anywhere in that combination. If we had a plant that was type 0, we could put in an integrator, a pure integrator in our controller to give us a type 1 system in the controller plant combination. For the full state feedback case, we mess up that system type by full state feedback. So we can't, even if we had a pole at the origin with full state feedback, we're going to mess that up. The only way we're going to get a 0 steady state error is to hope that we can select the N to give us a DC gain of 1 in our closed loop transfer function. And we're not even talking about robustness here, But if our plant or system happened to change, maybe the output feedback controller might be more robust than the full state feedback controller. That full state feedback is depending on all of these different parameter values to find a specific value of n. In the output feedback, all we need to know is we have a type 1 system, and even if the gains change a little bit, we're still going to be able to track the reference input with the output y. Suppose we also want a settling time of about 1 second and a percent overshoot of about 5%. As I said, this is kind of a review for the final. Closed loop poles. When you see that percent overshoot of 5%, what else do you see? I hope at this point. Do you see triangles at 45 degrees in the complex S-plane? If those are your dominant poles, those triangles, now you know where those are located. A settling time of 1 second tells you where sigma is, where the real part of those poles are, so that now you know that you need to be at least a distance of 4 into the left half plane to achieve the settling time spec. From the percent overshoot spec, from either figure 5.7 or these two formulas, you can figure out what theta is or what zeta is. In this case, you plug in a PO of 5 and you will obtain roughly 0.7 for zeta. Or if you just eyeball it from figure 5.7 and you read over what 5% corresponds to for zeta value, you're going to see it's about 0.7. With a 0.7 zeta, there's your 45 degrees. If the real pole or the real component of your dominant poles are at -4 and you have an angle of 45, that gives you your imaginary component of plus and minus J4. There's where we would want our dominant closed loop poles to satisfy a 1 second settling time and a percent overshoot of 5%, irrespective of whether we're doing output feedback or full state feedback if we had a second order system. Here's our output feedback. You could design this now, I hope, in your sleep. One, you've got all those index cards under your pillow, so you probably can even pull those out while you're sleeping and look at them and figure out what you need. But here we have G of S is 1 over S, S plus 1. What's the system type? I think I've been saying that. That's a type 1. We have the one pole at the origin. So this is where the 1 comes from. We have one pole at the origin. G of S is a type 1 system. What's our steady state error due to a constant if our closed loop system is stable? That should be 0, and here we're using a Cascade G of S. We're not introducing more feedback paths, so we're preserving that type 1 system with our G sub C of S, and we'll have 0 error due to a constant if we can just stabilize the closed loop system with G sub C. So now, can we make the root locus go through those triangles by the choice of poles and zeros of our controller? And now I should be seeing a lot of heads shaking up and down for the yes. Correct? Do you see this? What color do I want to make these? I guess I'll do them in blue. But how can I make the root locus go through those triangles? My design would say, let me cancel that pole at 1, at -1, which I can do. You can't cancel poles where? At the origin, on the imaginary axis, or in the right half plane. You can't cancel zeros over there either. But you can put poles and zeros in the right half plane or on the imaginary axis if you want. But now, hopefully you can see that the root locus looks like that for a controller, a Cascade controller with a 0 at 1 and a pole at 8. Am I done with that Cascade controller? No, I still have to pick K, or find K. Now that the triangles are on the root locus, I can at least select the K to get me far enough along that root locus to get to those triangles. I need to crank up the gain K. I'm adjusting this knob, and I now need to know how much do I adjust it to get me right to those triangles. What do I do to make that happen? I use the magnitude condition. I now know that to be on the root locus and to be a particular location on the root locus, I can make that happen by the choice of K. K times G sub CG, where now I've factored the K out of the G sub C. I now had this S plus 1 and I had an S plus 8. That factor cancels, so I don't even need to worry about that. But now I can have K found by forming the product of the magnitude of S when S is equal to -4 plus J4, and the magnitude of S plus 8, again when the S is -4 plus J4. Those are equal distance from each other, and now I just have 4 squared plus 4 squared, or a K of 32. So that now my Cascade controller that satisfies all of my design specs was pretty straightforward to design. And what's that controller? If I now ask you on a final, if I said, okay, here's a G sub C of S, is that a phase lead or a phase lag controller? All right, phase lead is thumb up, phase lag is thumb down. 1, 2, 3. Okay, we're doing better on the final on that question. That's actually a phase lead. Why? Because the 0 is closer to the origin than the pole. Here was our 0, here was our pole, and that structure, and we dramatically changed the original root locus. That's another characteristic of the phase lead design. What happens in full state feedback controller? We said we had our desired characteristic polynomial with roots of -4 plus and minus J4. We can find a polynomial that has those roots, and that's now our desired characteristic polynomial. Our desired characteristic polynomial is s squared plus 8s plus 32. We now need to set that equal to the characteristic polynomial associated with the full state feedback or the closed loop system matrix F, where F is now incorporating full state feedback in the form of, in this case, K sub 1 and K sub 2. Performing the algebra, there's F with yet to be determined K1 and K2. But if we form the determinant of Si minus F, we need then the determinant of this second order or this 2 by 2 matrix in terms of parameters S, frequency variable, and K's, K1 and K2. Doing that, we can see that K1 and K2 in general, K1 and K2 are going to be sprinkled in both the linear coefficient and the constant coefficient, so that we could end up with two equations in two unknowns. But we can solve that. That's a linear algebra problem. That's a 310 problem, correct? ECE 310. Two equations, two unknowns. We have two equations by equating the coefficients. We equate the coefficients for the linear term. We equate the coefficients for the constant term. And we end up with now two decoupled equations. K2 now becomes 7. K1 is 32. There's our full state feedback gain matrix, K. What's N? How do we find N? We found K. K is now 32 and 7, and you need to know that on the final. Hint, hint. If I now give you design specifications and say achieve these design specifications with full state feedback, you better be able to generate a K matrix. Or I could give you desired closed loop poles. You now need to find the appropriate desired characteristic polynomial by having those poles as its roots, and then equate coefficients with this Si minus F determinant. That being said, how do we define N? We know how to find K. How do we find N? Ideally, we want the closed loop transfer function between R and Y to have a DC gain of 1. Why did we want that? What's all this concern about a DC gain of 1? What does that do for us? Besides just being able to say that, now if we put in a constant for R, we would be able to track that with our output Y without any error. This is a little suspect when we don't know our system very well. So this has robustness issues, but here we're living in the ideal academic environment. We can find an N. But just be forewarned, in real life, if you find this N and you go, well, why am I not having zero error when I put in 4 for my input and my output's 4.7, what happened? Well, your system may not have been exactly like you modeled it to be. So you might have to adjust your N to make that error go away. You found that real-world systems based on the lab may not be exactly like what you think they are from your analysis, I hope. So now let's compute the reference input gain, knowing that we want T sub C of S at DC when S is equal to 0 to equal 1. And we know the formula for T sub C of S. That's right here. where this, don't know what color my marker is, there's F. There's the F matrix. That's our closed loop system matrix. And Y is just T sub C of S times R of S. Now, can you do this algebra? That's what's required. What's inside that matrix inverse is really just Si minus F. And you found F based on feeding back x sub 1 and x sub 2 through the gains. You know C, you know B. The only unknown now in this entire expression is this one parameter N. If you find that inverse of the matrix, you're dividing by its determinant. That's S times S plus 8 plus 32. So that gives you your characteristic polynomial that you wanted for a denominator, S squared plus 8S plus 32. What's going to happen when we multiply those three matrices together? You can do it in whatever order you want. If we multiply C first times the 2 by 2, we pull off the top row. And we have S plus 8, 1 in a top row being multiplied by 0, 1. Which will just pull off the 1, and so in fact we now have 1 over S squared plus 8S plus 32, all scaled by N. We want the DC gain to be 1, and that should be a very straightforward computation at this point. Can you tell me what N is if I want a DC gain of 1 before I go any further? N needs to equal that constant in the denominator, doesn't it? N needs to be 32. Well, if we set S equal to 0, boom, all of the denominator vanishes except for the constant. We have N over 32 equaling 1. N is now equal to 32, and what does that do for us? That gives us this input that we can now apply to the system. It gives us a closed loop transfer function of 32 over S squared plus 8S plus 32. That gives us our settling time of 1 second. It gives us a percent overshoot of 5%, and it has 0 error due to constant inputs with this U of T. What was U of S before? In the output controller case. What was U of S? Do you remember? There's U of S, isn't it? In our block diagram. In terms of E of S, do you now know what it is? U of S is just G sub C of S, E of S. But that was now this, was it 32? Boy, 32s are wild today, aren't they? It's occurring quite a few places. S plus 1 over s plus 8, and that was now multiplied by what? The error, which was r of s minus y of s. And y of s in this case was x sub 1. Now do you see that I'm actually filtering x sub 1? R is now not just 32, it's a filtered 32. And y, or x sub 1, is not just minus 32. Do you see how to compare the output controller strategy to the full state feedback strategy? We'll continue with this exciting discussion next time, or something thereof, getting you ready for the final exam, which is a week from tomorrow.